All right, so in this one, I will be talking about um, answering the question. And the question is, if you let go of two things which have different masses from a particular height, will they reach the ground at the same time, or the more massive one will reach first, or the lighter one will reach first? I'm gonna give the answer by two different ways. First, I will only make certain arguments, and the second, I will use a little bit of mathematics, a little bit of equations. So, I want to start with first just a case where we do not consider air resistance, okay? So, a case where we don't have air around. So, imagine a world where there's no air around, okay? And you have these two balls. This one is massive and this one is not as massive. So what's happening is you just hold them. Let's say you jump on a table, you're standing on a table, and from some height, you let them go. Okay. And then they will start moving down because the earth is pulling them down. Now, in order to make just arguments, I will have to give you a fact, and just to understand this, you can accept this as a fact. Or you can wait a little bit and I can also show you the mathematics of it or the physics of it. So the fact is that all the objects that are close to the surface of the earth, they experience the same acceleration. Okay, so all objects, this is facts, all objects, all objects closer to the surface of earth experience the same acceleration. Okay, so this one will experience the same acceleration, this one will experience the same acceleration. Now remember, when we talk about what will reach first to the ground, the concept of force should not really enter. Okay, what should come to your mind is whichever object accelerates faster to the ground will reach to the ground faster, right? So if you just accept the fact for now that all the objects experience the same acceleration when they're around the surface of the earth, then you can clearly see that this object and this object, when they are let go from the same height, they will reach the surface of the earth at the same time. Because they all start from the same height, they all start from initial velocity being zero because we are letting go of them, and then they acquire acceleration and they're moving down faster and faster, but they reach the surface of the earth the same time. Now this is when again there is no air friction, there's no this we are assuming that there's no air around. Okay, so what changes when there's air around? The thing that changes when air is around is acceleration remains the same towards the earth, but what you will see is that um, because this is a bigger area, like bigger volume, right? So it will catch more air. It will be more draggy. Okay, so it will catch more air, and this will catch less air. So this will feel a little bit of resistance because of the air. So this will lag behind very slowly as compared to this. So if I just let them go from a great height, let's say like a 10-story building, this will reach slightly before than this will to the ground. Okay, and this is when there is air. So if you just don't assume that if you just assume there's no air, then both of them, they will reach to the ground at the same time. But when air comes in, you'll have to look at which one experiences more drag or more like friction from the air. It's pretty much that. Now I'm going to talk about, I'm going to tell you exactly what I said in a very argumentative way. I'm going to tell you in a way which is more mathematical, which is more physical. Okay, so let's say if that doesn't make sense to you, then maybe this will. So we start with a simple thing where we say um, that what is that force that will be trying to, let's say I'm gonna make these two objects. Okay, so this is ball one, smaller one. This is ball two, a bigger one. Ball one has a smaller mass as compared to ball two. Okay, so smaller mass as compared to ball two. So what is that force that these two balls experience towards the earth? So let me make earth. So earth is really big, but let me just show you. Let me just really exaggerate this. We probably should get rid of this. Okay, that's the earth. So this will feel a force. I'm going to call that force F2. Okay, and then this will feel the force F1. Okay, remember, I'm not going to say ever that the force on this object because of the earth will be same as force on this object because of the earth. The forces are different on these two things, as you will see in a moment. But the point is, and I will show you mathematically, that the acceleration is the same for this one and for this one. So F2, let's say F1 is the force experienced by ball 1 towards the earth. What is that force exactly? Okay, that force is what we call weight of something. Okay, this has less weight, this has more weight, something like that. So that force F1 and F2 basically are the weights of ball number 1 and ball number 2. Okay, so if I just think about F1 for a moment, F1 is W1, which is the weight of the first one. Okay, and F2 is W2, the weight of the second one. Now the weight is given by mass, I'm going to write it here, times gravity, that is small g. Okay, so weight is m1, let m1 be the mass of the smaller ball. Okay, and that times small g. And for w2 it will be m2, mass of the second one, times small g, that is f2 and that is f1. Now there's something called Newton's second law, which tells you acceleration if you know the force and force if you know the acceleration. So Newton's second law, the equation from the Newton's second law, I'm going to delete a little bit of the earth here so because I need more space. The equation of the second law, and then you will use this throughout the semester, and that is F force is equal to mass times acceleration. Okay, force is equal to mass times acceleration. So F1 will be equal to mass of the first ball times the acceleration of the first ball, right? The second force will be equal to mass of the second ball times the acceleration of the second ball. So what I can do is I'm going to use these two equations. I'm going to write those equations in this box. Okay, I'm gonna do a substitution. This is F2, where I'm gonna substitute the value of F1 from this equation here, and then value of F2 from this equation here. So I've got F1 is equal to M1G, and I've also got F1 is equal to M1A1 from the second law, Newton's second law. Okay, so I can replace F1 here by M1A1. So when I do that, I get M1A1 equals to M1 times G. So this means that if I divide both sides by M1, M1 cancels here, this gives you the acceleration of the first ball is equal to G. Now let's do the second one. So now we know that the acceleration of the first ball is equal to small g. Let's look at the acceleration of the second ball. So for that, I start with this. F2 equals to m2g, and F2 is also equal to m2 times acceleration. Do the same thing, substitute it here, and you get m2 should be a2, that is the acceleration of the second ball, is equal to m2 times g. Divide both sides by m2 like we did here, and we get a2 is equal to g. So as you see, I have proved using Newton's second law that the acceleration of this ball and the acceleration of this ball is the same. Okay, so if you let go of those two balls from the same height, what you will see is that they both will reach to the ground at the same time, because they have the same acceleration. They were dropped from the same height, and the initial velocity was zero. And again, I mean, I just want to stress this is really important, and this is when the air resistance is not there, or there's no air around it, okay, around the balls. But what happens when there's air around the ball? So what happens when there's air around the ball is, you know, let's say this is the first ball. Sorry for a weird cut there. My mic's battery ran out, so I had to recharge it quickly, and now I'm back again. So what I was talking about is we saw mathematically here that the accelerations are the same. So when you don't consider air resistance, and this is really important, the acceleration is the same. So if you just pick them up and then you release them from the same height, they're going to reach the ground at the same time, because initially their height is the same. That means they have to cover the same distance. Their velocity is the same, which is 0 and 0. Okay, so and then their acceleration is the same, so that means they're going to reach the floor at the same time. Now what happens when you have air resistance is pretty much the same thing that happens when you, for example, when you take your hand out of the window in a moving vehicle and you do this, right? So the air is coming in here and you do this. So what you feel is some resistance, right? But if you do this, that means more air is now able to, like, literally bombard on your hand. That's how the air is pushing your hand behind. You feel that pressure, you feel that resistance, right? So you can clearly see when the area is less, the resistance is less. When the area is more, the resistance because of the air is more. So when you have a case where, let's say, you have two balls, one is smaller and then the other one is bigger, then more air is caught by this bigger ball, right? More air is, like, the area is bigger, so the resistance because of the air on this ball is more. So if there is, so that means that this ball, because I mean it really wants to go with the acceleration small g, it is going with small g, but what is happening is that air here is creating less resistance as compared to air here. So this ball, the bigger one, slows down just a little bit, but slows down technically. And this one will reach first if there is air around. Now, you don't really see this in a laboratory setting, because in a laboratory setting, usually we drop these things from, let's say, 8 feet, 10 feet high, right? Not the distance is just not high enough for this to really speed up, and this to really lag behind. So we don't really see both of them, this one reaching first and this one reaching later. But if you, let's say, climb in a 10 on a 10-story building, and you, from the rooftop you're just releasing these two balls and there's air around, then the air resistance will be more on this one as compared to this one. So it's going to lag behind just a little bit. Okay, the higher the height is, the more pronounced this effect will be. So really important when we consider the air resistance and when we don't consider the air resistance. All right.